Hello. Hello.
Yes, because.
Hello. Good evening, everyone. I, Vikas, going to give a brief introduction about the expert of today's session, Dr. Arvind Kumar Prajapati, who will give you deep insight of reduced order modeling and the controller design using MATLAB. Dr. Prajapati is working as an assistant professor in electrical engineering department, MNNIT Allahabad, Prayagraj from January 2025 onward. He received his bachelor's degree in 2013 from Umanath Singh Institute of Technology, Bir Bahadur Singh, Purvanchal University, Jaunpur, Uttar Pradesh, in electrical engineering. He received his master's degree from NIT Silchar, Assam, in electrical engineering with the specialization of control and industrial automation in 2015. Subsequently, he obtained a PhD in electrical engineering from IIT Roorkee, Uttarakhand in 2019 with the specialization of system and control. He served as a senior assistant professor in electrical and electronics engineering department, Madan Palve Institute of Technology and Science, Madan Palve, Chittoor district, Andhra Pradesh, from June 2019 to December 2019. He worked in a Bangalore Institute of Technology, Andhra Pradesh campus, VIT-AP, from January 2020 to October 2022 as an assistant professor grade 1 in School of Electronics Engineering, where he also worked as a research coordinator. He served as an assistant professor in electrical uh, engineering department NIT Jamshedpur, Jharkhand from October 2022 to January 2025. He has received 14 awards based on his academic performance. He has published the three Indian patents, 16 SCI, 16 SCI journals, paper, 19 international conference, 3 book chapters, and 1 book. He has more than 5 years experience in teaching and research. He is an active reviewer of the several transaction journal and conference. His current research focus on the area of model order reduction and its application, fault detection and accommodation, and integrated vehicles health management IVHM system. Now I warmly welcome and invite the Dr. A.K. Prajapati sir to deliver his session. Thank you. A.K. Prajapati sir.
Yeah, so thank you, Vikas, for nice introductions. So I hope my slides are
Thank you, sir.
visible. And
Yes.
good evening, everyone. So today's lecture I'm going to give on the reduced order modeling and controller design using MATLAB. So in the today's lecture, I will just discuss some introductions about model order reduction techniques, reduced order modeling, and then by using reduced order modeling, we will also learn how to design the controller. So before going to start like what is reduced order modeling or model order reductions, we may have to know why we are going to learn this topic. So as we know today's era, we are demanding particular systems must perform multitasking. Like if we are using mobile, in the earlier days, we are using mobile for the purpose of talking and calling purpose. But nowadays we are using mobile for many tasks. So if we will increase the functions of the systems, then the complexity of systems will definitely increase depending upon the properties or how much tasks you are going to be take from that systems. So if the system multi functions will increase or if systems are going to perform multitasking, definitely the complexity of that system will get increased. And as a system engineer or as an engineer, it is difficult to do the analysis of these complicated systems. If your systems is very simple, then anyone can just do the analysis and then they can discuss about the systems. Yeah, this is this system and there are these components, and if there is a fault, so these components are getting faulty. But if the system is very much complicated, then as a human being, we are unable to do the analysis of that system. So you may do the simulation by using some softwares like MATLAB or any other softwares. And if the system is complicated, then MATLAB also may take more time to do the simulations. So it is difficult, like if you want to prompt response that I want to know the systems immediately, then it is difficult if system is very complicated or large scale systems, okay, or higher order systems. So how these higher order systems we can replace simple system, and if you are replacing higher order systems into the simple systems, then what properties we have to preserve or what properties reduced order system or simple system must preserve that reflect the higher order systems. Means if you are going to replace equivalent reduced order system or a higher order system, then the equivalent reduced model or a simple system must reflect the fundamentals or dominant properties of the higher order system. To do this, there are several techniques for replacing the higher order or complex systems into the simple systems. So these techniques are called as a reduced order modeling or model order reduction. So model order reduction we can simply define as a process or technique to replace the complex systems or complicated systems or higher order systems into the simple systems, that is known as reduced order model or simple abated model, which have the fundamental properties of original systems, as well as it also reflect the properties of the original systems. So suppose if your original systems is giving steady state values like 10, so your reduced model must also give the steady state values as a 10. Similarly, if your like original system is stable, then your reduced system must also be stable. So these are the like conditions for if you are doing the model order reduction. So if you are going to learn the model order reduction, so before going to learn the model order reductions, you must know what is large scale system. So large scale systems is defined as a systems which is having more than like 100 variables or 100 elements, or which is having thousands of equations for representing a particular system. If we need like several equations or several variables to represent that system, then that system is called as a large scale systems. So the large scale systems are exist not only in the electrical engineering, it is exist in the various fields of engineering like in the mechanical engineering or in the chemical engineering or in the biomedical systems or thermodynamics or in the electrical engineering like in the control system, power system, etc. So the higher order systems are exist in various areas of engineering and sciences. To do the analysis and parameter estimation of these systems, it is difficult to do the manually. So if you will use some softwares like MATLAB or any other softwares also, so it may also take several hours or several days to do the simulation. To overcome these, the model order reductions are proposed, and that initially model order reductions was proposed in 1967, and after that several works are running on in the model order reductions. So the model order reductions plays an important role for the simplifications of higher order systems. So how it will play an important role? It will help to do the analysis of that large scale systems, to do the synthesis of large scale systems, and also helps in the controller design or to make help in the automation of complicated systems by approximating that complex systems into an equivalent lower order systems. So there are several requirements to do the model order reductions. So if you are doing the model order reductions, then model order reductions must reduce the complexity. Means if you are proposing some model order reduction techniques, so your model order reduction techniques should not be very complicated, because model order reduction is we are using for the simplification purpose. Means if system is complicated, we are going to replace that system to its equivalent lower order system. So for doing this, we have to use some simple algorithms or techniques, and that techniques or algorithms we called as a model order reduction techniques or reduced order modeling techniques. And also, if you are going to reduce the hardware complexity, then we will require model order reduction, because if your original system is having like 1000s of variable or 1000s of equations, so in that proportional you will require hardware components. But same systems, if we can replace by a simple systems, then that systems can be represented by less number of components. And also, if you want to capture the essential features of the large scale systems in short period of time, then it is possible only if you are going to replace large scale systems into the smaller scale systems. And also for better understanding of the large scale systems, suppose if your large scale systems are having very complicated or having several components, so it is difficult to do the learn or analysis of all those components. So model order reduction will help for the better understanding of large scale systems by replacing large scale systems to its equivalent reduced order systems. And also, like if you are going to design the controllers, so if your systems is having order more than 3, then it is difficult or sometimes it is impossible to design the controller. If you are unable to design the controller, then you may unable to make the system automatic or automation. So in order to overcome these limitations, you can replace large scale systems which is having higher order more than 3 into a lower order systems which is having order less than 3. If the complicated systems which is having order more than 3, if you are replacing it into a order which is less than the order 3, then we can easily design the controller for that reduced order models, and then that controller we can implement in the original systems. And also for the online implementations, if we will use model order reduction, then we can economically we can implement online. So if you are doing the model order reduction, then what will be the requirements for the model order reductions, or whatever the what is the requirements for doing reduced order modeling. So if you are doing the reduced order modeling, so first thing is that the behavior between original systems and its equivalent reduced systems must be equivalent, means the behavior of original system and reduced systems will be approximately similar. Then only we can say that model order reduction is working, and then that is the model order reduction technique. If you are replacing some systems like complicated systems into a simple system by using some techniques, and in that techniques if you are getting errors which are very high, or by watching reduced order system performance, if you are unable to replicate it with the original system performance, then we can say that model order reduction technique is not good, and we will discard that techniques. So here we are talking about the reduce order computation, to reduce the approximation error. So what is the approximation error? So I will just tell here how you can just determine the error. So suppose if your system is there, in that system you are giving step response. So this is my step response of the original system. Why we are taking step response? Because most of the signals we are using as a step signal, and then this is our system in which we are giving like steady state values like 240 volts. So our output is getting this 240 volt. Then we have used some techniques of model order reduction, so that we are getting steady some deviation from the original system's characteristics. So the deviation between these, that is error. That is the error. So these errors should be limited. That error should be not be very high. If it is very high, then that method is not good. Okay, and then that method we will not use in the model order reduction techniques. So how you will calculate the error by using MATLAB, I will tell later how you can calculate that error using the MATLAB. Second requirements for the model order reduction technique is that if you are proposing new model order reduction technique, or if you are using some model order reduction technique, then that model order reduction techniques must preserve the fundamental properties of the complex system. So fundamental properties of the complex system means like stability. If your original system is stable, then your reduced system must also be stable. Otherwise, that method is failed. Okay, we will ignore that method. We will not use that method. And also, we will prefer the method which are giving same steady state value. Suppose if original system is giving steady state values like 240 volts, and you are using some order reduction technique which is not giving near about 240 volts, then that method we will not use. Similarly, like in the fundamental properties is like if your original system is controllable and observable, then your reduced system must also be observable and controllable. And overall, the contribution is like that. Whatever the methods you are using, or whatever the methods you are proposing for the model order reduction, that must be computationally efficient. It should not be very complicated or lengthy. So now we are going to do how to do the model order reduction. So for doing the model order reduction, we can do either in the for the linear system, we can do either in the transfer function form or in the state space. So for the transfer function, first we have to know the transfer function of complicated system or large space system. So equation 1 is representing the transfer function of original system, and which is order of n. So the order of n is what? It is very high. It may be order of like more than 10, it may be more than 50, more than 100 or 2000 or more than 1000 also. So depending upon the complexity of that system, the order of the transfer function is very high. So suppose this is the like order of fifth order system. So if it is fifth order system and anyone asks, check whether the system is stable or unstable, and you don't know the route stability. So how will you determine whether the system is stable or unstable? So you can determine by determining the poles of the system. So if it is fifth order system, then you may not able to determine the poles of that system by using calculator also, because now you may determine the poles of the system which is having order 4, but if it is a system having order more than 4, then you cannot determine the poles of that systems by using calculator also. So how you can comment whether the system is stable or unstable? So you can use model order reduction technique, convert the system which is having more than order 3, you can convert it into second order, third order, and then you can determine the poles of the system, and according to the poles you can comment whether the system is stable or unstable. So the second equation is representing the transfer function of the reduced model. So the goal of the model order reduction technique is to replace the equation 1, which is having order n, by a equation 2 that is representing the transfer function of reduced model, and its order should be very less than the order of the original system, that is n. So where n is very high as compared to the order of the reduced order model, that is r. So this is the like problem statement of model order reduction in the frequency domain. So in the frequency domain, what will be the given? Given is like transfer function will be given. So our motto is to calculate the transfer function of reduced model by using some techniques. And in the time domain, if you are doing model order reduction in the time domain, so first we have to represent the complex systems into a state space model. So equation 3 is representing the state space model of any large scale system, and which is having order n. So the main objective of the model order reduction is to replace the state space model given in equation 3 by a state space model given in equation 4, so that if we are giving same input which are giving in the original system, same input if you are giving in the reduced system, so we must get approximately the same response. Then the technique for reducing, replacing equation 3 to equation 4 is okay, and then that technique we can use. So, and that technique we are going to learn in next slides. So, how to reduce state space model, large scale systems into another state space model, reduced order systems. So first technique we are going to learn in the model order reduction technique is the frequency domain technique, and that is the route stability technique. So why I am going to take this technique? So this technique was proposed in 1979, but it is very simple technique, and it was proposed by Sesadari and Krishnamurti. So this technique is very simple, and everyone is familiar about route stability technique. So why we are using route stability method? So we are usually using route stability method for checking the system is stable or not stable. So how you are using route stability? So if the system's characteristic polynomial is given, so you have to construct the route stability table, and then from the route stability table you may comment the system is stable or unstable by watching its first column. So in the first column, if any rows is having negative elements, then we can say yeah, the system is unstable. And if all the elements in the first columns are positive, then you can say the system is stable. So same technique here we are using in the model order reduction. So how we are using? So I will tell here. So first we will apply the route stability technique or route stability recursive formula by constructing the denominators stability table. So how you can construct? So the denominator of the higher order system will be given. So from the given higher order systems of large scale systems, we will make two rows of the route table by using denominator polynomial of the large scale system. So here it is what it is, just like s to the power ns coefficient, it is s to the power n minus 2s coefficient, it is s minus n minus 4 coefficient, and it is s to the power 0 coefficient, like that. Okay. Similarly, this will be like s to the power n minus 1 coefficient, and then it will be s to the power n minus 3 coefficient, depending upon the value of n is even or odd. So in that way. So these are representing. So like rows 1 and rows 2 are representing the coefficients of the large scale systems denominator polynomial. So after writing these two rows, next element we can calculate by using route recursive formula that you already know. This is given here. This is the route recursive formula, which is like saying that for determining this element, you have to multiply this element into this element, and then subtract the multiplication of these two elements, and then divide d2 upon d2 1. So you will get d3 1. Similarly, you can do the multiplication this element with this element, and then subtract this element, and divide d2 a1, and you will get d3 2. Similarly, you can calculate d3. And for calculating d4 1, so you can again use this next two rows, and then cross multiply, and then divide it by the first column's coefficient, and you will get d4 1. And similarly, you can complete this table. So this table you already know. This table is similar as you are using for checking the stability. So after constructing these tables, you can just take the coefficient, desired coefficient. So suppose if I want to determine, like we are going to replace ns to the power ns coefficient, means polynomial, into a second order polynomial. So what will I do? I will just take the s to the power 2 coefficient, then some plus or minus s to the power 1 coefficient, plus or minus s to the power not coefficient. So everyone is knowing this is the s to the power s not coefficient. Sorry, we will take these rows. So from these rows, so this is representing the s to the power 1 coefficient, this is representing the s to the power 2 coefficient, and this is representing the s to the power not coefficient. So which rows we have to take, so that you can check by using these formulas. So this rows. So by using these rows, you can construct the characteristic polynomial of your desired reduced model. Desired reduced model means we are going to calculate the characteristic polynomial having order r. So this is the polynomial of rth order reduced model. And then if you know the denominator polynomial, similarly, same you can also apply in the numerator polynomial. So first two rows of this numerator polynomial we can directly write by watching the numerator polynomial of the original system, and then next other elements you can calculate by using route recursive formula, which is given here. And again, according to our requirements, we can construct the numerator polynomial of the original system. So sorry, reduced system. So these are the numerator polynomial of the reduced systems. And if you know the numerator polynomial, if you know the denominator polynomial, so you can write your reduced order transfer function. So this is the reduced order transfer function. So again, okay. So next, in order to calculate your reduced order systems with other existing techniques, we are going to calculate error. Means what is the error? So error is just difference between like response of original system and the response of reduced system. So this is the response of here I have taken like step response of original system, and this is the step response of your reduced systems. And after that, I have taken relative integral square. By using these formulas, we can compare the relative integral square error of original system and the proposed reduced order models. And then there is two more additional performance error indices is also calculated by using these formulas, and that is known as integral absolute error and integral time absolute error. So these four performance error indices are used to calculate the error between original system, quantitative error between original system and the reduced system, means how much error you are getting as with respect to original systems. And so this is the like example of a real-time systems that is called like single area power system model, and which is modeled in the reference number 5 and 61, in which a single area power systems model or modeling has been done, and then that is finally converted into a transfer function of order 3. So here I'm going to convert this third order transfer function into a second order system. So how we can do it? So because we have just learned route stability method, so we can do it by using route stability technique. So how you can do it? So I'm just going to tell you. Yeah. So you can just take like here I'm just going to tell you how you can do. So this is just like a transfer function of 250 divided by like s cube. Just for example, like 10 years square, and then 15 years plus 2. Now I want to convert it into a second order system. Yeah, we can write here also some other transfer function like s square plus 10 years plus so here if you will see the steady state value at s is equal to 0 is 1, because here the constant coefficient is 1 only. Okay. So now what we will do, so we will apply route stability method in the denominator. So in order to apply route stability method, so we will first row, we will write the coefficient of higher order, that is 1, and then next coefficient is 15, and then completed. Then you have to write s square coefficient by watching this polynomial. So it is nothing but 10, and then another one is 2. So now rest other rows we can calculate by using route recursive formula. So what is the route recursive formula? You can just multiply 10 into 15. So if we multiply 10 into 15, so you will get like 150 and then minus 2 divided by 10. So you will get what? You will get like 14.8. Okay. And then this is 0, and then you can calculate s naught. So s naught if you will calculate, so you will get 2. So now I want to write second order denominator polynomial by watching this. So how you can write? So we will take just these two rows, and then we can write the denominator polynomial. So by watching these two rows, so what is the coefficient of s squared? So it is the coefficient of 10 s squared. Then this is the coefficient of s to the power 1. So it is nothing but 1.4 s, and then you have to write the coefficient of s naught. So s naught coefficient is this 2. So this is the coefficient of 2. So this is the denominator polynomial of second order reduced model. Similarly, you can you can make route table for the numerator, and then you can also write. So if your denominator is s to the power 2, so we will take like s to the power 1 as the highest coefficient in the numerator, and then you can write the coefficient. So you will get approximately like you can just apply and you will get this. So once you have calculated your reduced order model, and this is your original systems, GS is the original system and RS is your reduced system. So you can just calculate the error. So how we can calculate the error? So we can just calculate the step response of the original system for a particular time duration. So that we will write like YT, and then YR we will calculate the step response of the reduced systems. And then you can just calculate the error is equal to y minus yr, and then integral square error is nothing but e into, this is just like a, you can give just capital E. So E, capital E into E dash, that is nothing but the integral square error. Okay, and then in that way we can calculate the integral square error between original system and reduced system. Similarly, you can also calculate by using these formulas relative integral square and integral absolute error, integral time absolute error. So once you have calculated reduced order model by using some techniques, then you can compare your techniques with the other techniques. So here I have compared with these techniques with other techniques. So here, like if you will see, like I have proposed some new methods. So in which you can see that these methods are giving the less error as compared to the other existing methods. So I have just prepared the tables. So I have just like here I have used like in this column I have mentioned the name of the techniques by which I have taken this reduced order model, and then I have calculated the integral square, relative and absolute, and then integral time absolute error on the basis of descending order. So here you can see like the route stability method is giving this much error. So I have proposed the techniques in which the error is little bit higher, but that proposed method is overcoming the problem of route stability method. So what are the problems in the route stability method? I will discuss in the next slide. And then I have also compared the proposed method of reduced order model with the existing technique in terms of step response. So these are the step response of the original systems and then reduced systems. So here you can see the step response is what the response of the original system and the response of the proposed systems are overlapping. Means the method which we are using for determining the reduced order model is okay or good as compared to the other existing methods. Then, in order to overcome the route stability methods problem, a new method is proposed. So, what are the route stability problem? So, like if there are several large scale systems, like the large scale system G1 or G2, by using a model order reduction technique of route stability method, we may get the same reduced order model for different higher order systems. So that is called uniqueness problem. This uniqueness problem will be overcome by using another method that is given in the next slide. And then there are some other techniques. There is and the drawbacks of route stability is that sometimes route stability method unable to preserve the dominant characteristics of the original system. Yeah. So to overcome that, the another method is proposed. This will be discussed in the next slide. So to overcome this, a improved route stability method is proposed. In these techniques, what we are doing, we are just taking the like original systems, denominator and numerator. In the denominator, we are applying the route stability method. So by applying route stability method, we are constructing this table, and by using these tables, we can determine the denominator characteristics of the reduced model, which is given here. And then numerator, we are going to determine by using comparison method. So how we are comparing? So here, this is the transfer numerator polynomial of the original system. This is the denominator polynomial of the original system, which are known. And next is this one. This one is the your transfer function of the characteristic polynomial of the reduced model, and this is also known, which we have calculated by using route stability method. So numerator we are going to calculate by using comparison method. So what you can do, you can just cross multiply this into this. So these are the known, these are the known. Only Q0, Q1, Q2 coefficients are unknown. So if you will cross multiply, then you can just solve these simultaneous equations. You will get the unknown coefficients of the numerator polynomial. So if you will do this, so you can just apply in any like a fifth order stable systems in which the denominator we have calculated by using route stability, we are getting this, and the numerator we are just cross multiplying, and then we are getting this. And then these techniques, this is the reduced model by using proposed method is compared with the response of original system as well as the response of other reduced model techniques. And then if you will see, then this method is giving least error as compared to these techniques. And then if you will see the step response, so this is the step response of the original systems and the reduced systems. Then similarly, like the previous method which I have discussed, that is called like route stability methods. Here we are going to learn that is called like a route approximation and factor division algorithm method. So here route approximation is similar as a route stability method, but here is so many differences there. In the route approximation method, we will use alpha and beta table. So alpha and beta table is little bit different as compared to the route stability method for calculating the reduced order model. And why we are using route alpha and beta table? Because there are some limitations which are in the route stability. To overcome that, and we are going to learn route approximation method. And the numerator we are going to determine by using factor division method. So for applying the route approximation method, how you can get the reduced order model? So first you have to take your original transfer function and then choose your denominator polynomial and then do the reciprocal of the denominator polynomial as did in the equation 3.1. So how you can do? You can just replace yes by in the denominator polynomial of the original system. You can replace by yes by 1 by yes, and then you can multiply by s to the power n. You will get the modified denominator polynomial of the original system. And then by using this modified denominator polynomial, we will make the route stability table as given here, and that is called as the alpha table. And then we will use the formula which is mentioned here. By using these formulas, you can calculate the coefficients of the first column, second column, and rest other column. And then here starting two rows are again it is known and which are obtained by using equation 3.2. And then rest other elements you can calculate by using route recursive formulas, and then you can determine what is the value of alpha 1, alpha 2, and alpha 3 by using these formulas. And by after determining the alpha 1, alpha 2, you can determine the denominator polynomial of the reduced model by using this equation. So here you can just put the what is the value of alpha r, what is the value of pr minus 1, pr minus 2, for putting different values of r, and where p naught and p minus 1 the value is 1. So and by using these and by using alpha 1, alpha 2, alpha r values on the next slide of the table, alpha table, and then you can construct the characteristic polynomial of the reduced model. And then after determining the characteristic polynomial of the reduced model, next task is to determine the numerator polynomial. So in the in original route approximation method, numerator is also determined by using beta table, which I am not here going to discuss. I am going to discuss another technique that is called factor division algorithm. Yeah, similarly, if you can determine beta table and then you can use numerator polynomial equation and you can construct the numerator. So numerator and denominator you can calculate by using route approximation method. But there are some drawbacks in that techniques. What are the drawbacks? Because route approximation technique is applicable only and only when the numerator and denominator polynomial order difference is 1. If the order of difference is more than 1, then it is difficult to apply or you cannot apply the route approximation method. Then we are going to apply factor division algorithm for calculating the numerator, and that I have discussed here. So here again, this is the QR, that is the polynomial of the reduced model, which is not known. And then numerator of the original system, this is known. This is the denominator of the original system, this is also known. And then this is the polynomial of the reduced order model's characteristic polynomial, and that is also calculated by using route approximation. So all these are known. So if you will multiply, then you will get this rational function. And in these rational functions, we will do the Taylor series expansion about s is equal to 0. Then we can get the coefficients. And then we can get the coefficients and we can determine Q naught, Q1, Q2 by using here, which is given here, alpha naught, alpha, like A naught, A1, A2. And then D naught, D1, D2 is the denominator of the original systems, and then alpha a naught a1 a2 is calculated by Taylor series expansion, and then you can calculate what is the value of q naught, q1, q2, and qr. And so if you are able to calculate this q1, q2, q naught, qr value, means you are able to determine the numerator of the reduced model by using factor division algorithm, and then you can get the reduced order model, and then you can compare your method with the other existing methods. So here I have implemented these techniques in the Cuck converter. So what is the Cuck converter? So Cuck converter is like a transformer, like in the AC there is a transformer. Similarly in the DC there is a transformer that is called Cuck converter, means which can increase the voltage as compared to the input voltage, or which can decrease the output voltage as compared to the input voltage. So it will work like a buck boost converter, and the electrical circuit diagram of this converter is given here. And then if you will do the mathematical modeling of these systems, when it is like a switch is on, where this is the switch, when switch is on, then this is one circuit and the circuit will be this, and then you will do the mathematical modeling, you will get one state space model. And similarly, if switch is not on, then the circuit will be like this, and then you will get in the state space model. And then they for this one system there is two state space model, so we will use state space averaging technique, which is discussed here. By using these formulas, we can convert two state space models into a single state space model. So now you are getting the state space model of the real-time systems, and then this state space model, if you can convert into transfer function by using MATLAB or manually, then you can apply transfer function techniques. Otherwise, you can apply time domain technique in this equation. And these are the parameters which I have taken. After taking these parameters and then converting that is time domain into frequency domain, so I'm getting this transfer function. And then if you are going to calculate the steady state values, so if you will do this division, so you will get this steady value. Just other I have calculated by using Taylor series expansion. So Taylor series expansion of this polynomial is given this, where these are the known as time moments proportional. And then why we are going to show this, I'm going to show that if you will use like proposed techniques, so the reduced model will also give the same approximately same time moments. Starting few time moments will be the same. So next, how this is the original system. So how we will calculate the denominator polynomial. So as discussed in the route approximation method, you can first reciprocate the original denominator polynomial and then apply alpha table. And by using alpha table, you can use these characteristic equations, and then you will get the characteristic equation of the reduced model. And by using these characteristic equations, and then you can use vector division technique, you will get the reduced order model. You will get the numerators reduced order model, and this is your final second order reduced model of your Cup converter. Original Cup converter is like fourth order, and here you are getting second order Cup converter. So if you will see the response, so you can see the response of both the systems are same. So if the response of both the systems are same, then why we are going to design the controller for this fourth order system? Because it is difficult and it will be time consuming. So we can design the controller for this system, and then we can implement in the original system. So, and this is the comparison of your proposed method with other existing techniques. So here I have compared many other techniques. Then we are getting some errors. So in that way, you can also propose some techniques, and then you can also compare. And if you are getting least error as compared to the some existing techniques, then you can also get the publication. So these are the publications which I got on the model order reduction technique, which is based on the dominance mode. Dominance mode means like in the denominator polynomial, there will be some poles which are dominating the characteristics of the system. And then here I'm going to discuss the techniques which are based on that techniques. So like here I'm going to discuss like pole clustering method. So pole clustering method was originally proposed by Jan Topol. So in this technique, what he has done, like he has just calculated the like denominator of the original system is given here. So it is like having poles P1, P2, and P3, and so on. So what he has done, so he has just make the clusters of poles. So like P1, P2 in one cluster, P3, P4 in one cluster, and then he has calculated the cluster centers of these clusters, and these cluster centers he has used are calculating the denominator of the reduced model. And similarly, he has also did for the numerator and then calculated the numerator by using these clusters. So what is the drawbacks here? So like if the original system is having two dominant pole or three dominant pole, so in original pole clustering methods, all the dominant pole will become in one cluster, and just other clusters will having only undominant pole. Means in this method only be having this method is retaining only one dominant pole, rest of the dominant pole are discarded. So to modify these and the techniques I have proposed, that is called like generalized pole clustering technique. So why it is generalized pole clustering technique? Because for the particular value or for particular values of the variables, this generalized pole clustering technique will become similar as a pole clustering technique. That's why it is called a generalized pole clustering technique. The process is approximately similar as a original pole clustering technique. So what we have to do, first we have to make the clusters. For the clusters of poles and zeros, you have to make the different clusters, and then you have to group the, like how you can group. So like real poles and complex poles are clustered separately, and separate clusters should also made for the poles lying in the left half S plane and the right half S plane, and the poles which are at the origin or imaginary axis, which will be kept directly in the reduced order model. So here I'm going to discuss the how you can do the reduced order modeling by using pole clustering technique or generalized pole clustering technique. So for applying these techniques, you have to convert your Vergennes transfer function into a pole zeros form. So here I have converted the transfer function of Vergennes system, which is polynomial ns and polynomial ds, in the form of poles and then zeros. And then here you are having, you are knowing the poles of the Vergennes system, and then if you are knowing the poles of the Vergennes system, so what you can do, you can just make the cluster. Means first you have to make the cluster. Cluster means grouping the poles. So how I had did the poles? So first we had to arrange the poles in the ascending order of their magnitude. So all the poles are arranged in the ascending order. Then in the first cluster, first poles are placed. Second clusters we are putting in the second cluster. Then third poles are placed in the third cluster. Similarly, rth pole are placed in the rth cluster. Then again we will repeat. After rth pole, then r plus 1th pole we will keep in the cluster 1, then r plus 1. So why we are doing this way? So if you are doing in this way, then like starting, because it is in the ascending order, so these are the dominant pole. So these dominant pole are now going in all the clusters. So if you are doing this way, then you are keeping r dominant poles of the original system in your reduced model. And then by using these formulas, you can determine the cluster center. And then if you, once you have calculated the cluster center, you can calculate the denominator of the reduced model by using these clusters. So now you are getting the cluster characteristic polynomial of the reduced model. You can determine the denominator. So similarly, you can determine the denominator, and then you can get the reduced order model by using generalized pole clustering method. But here I have discussed generalized pole clustering method and factor division algorithm. Means the denominator is calculated by using generalized pole clustering method, and factor division algorithm is used for calculating the numerator polynomial. So what here is again, this is the numerator of the original reduced model. NS and DS are the original systems, which are these polynomials are already known, and these we have calculated by using generalized pole clustering method. So if you will just do the multiplications, we will get this transfer function, and then if you will expand this transfer function about s is equal to 0, you will get the coefficient a naught, a1, a2, and then you can just use these formulas which is given here. By using these formulas, you can construct this modified Routh table, and then you can calculate the coefficient of the numerator polynomial q1, q2, qr minus 1. And once you have calculated the numerator, means you are calculated the reduced order model. So once you have calculated the reduced order model, then you can compare your method with the other existing method in terms of like either quantitative term. Quantitative term means you can calculate the error and then you can compare, or you can calculate in the qualitative form, means you can compare the step response. You can see the step response of original system and the step response of your method, and then you can conclude, yeah, whether the system, means your method is giving good results or not. So here just I have used the techniques which I described, and then by using these techniques I have calculated the denominator, and then after calculating these denominators I have used like factor division algorithm. Then you can calculate the numerator, and then if you will see the response. So these are the response of the original systems and the response of the reduced systems. So like here, blue one is the response, which is here, which is overlapping with the response of the original system. So blue one is the proposed method's response, and green one is the response of the original system. So both the response are matching. So it is satisfying the objectives of the model order reduction. So proposed method is working good. And so what is the, like, what is how we can say that? So like, you know that the model order reduction technique is what? It is a technique which is replacing the original system, means complicated systems, into the simple system in such a way that simple system will reflect the same response as the original system. So here the original system's response and the reduced system's response are overlapping. So we can say that the proposed method is giving good result. So here I have just compared the different method with the existing techniques. Then you can say the error is giving list by proposed method and as compared to the other existing techniques. So similarly, you can apply in the multivariable systems also. If you will apply multivariable systems, so you will get these equations, and then you can also compare in terms of time domain or in terms of quantitative, in terms of error. So now I'm going to discuss some techniques which are useful in the time domain also. Like in the frequency domain, you have seen some techniques which you may know also, like route stability technique that you already know, that you may know, but some other techniques you may not know, like uh, some other techniques like by pole clustering techniques or other techniques you may not know. So that I already told here. So next we are going to learn the technique which are used in the time domain. So in the time domain, one of the most frequently used technique is the balance truncation technique, which is widely used for the reduction of large scale systems in the time domain. So, who has proposed this technique? Initially, this technique was proposed in 1981 by Moore, when he has observed that the dynamical behavior of the system is unbearable if we will truncate, if we will ignore the least controllable and least observable variable of the system. Means if you are going to plot the response, so you are plotting the response, and then if you are able to determine which are the least variable, least controllable and least observable part or variable, then you can ignore that least controllable and least observable variables. If you will ignore that, then the behavior of the system is approximately same as the behavior of original system. So he has proposed that technique that is called balanced truncation technique. So how he has calculated least observable, least controllable part. So for that we have to learn these techniques. So the balanced truncation is based on the four concepts that is called, like, first you have to know or to determine controllability and observability gradients, and then you have to also learn how to do the factorization, lower matrix factorization, means how you can convert your partially definite matrix into lower tabular matrix, and then you may also know you may also have to know what is the singular value decomposition, and then balance realization. If these four concepts you are knowing, then you can implement balanced truncation method in the model order reduction technique, and you can get the reduced order model. So in the balanced truncation techniques, having some problem for the systems, for the some systems, the response of the original systems, like suppose this is the response of the original system, the response of reduced systems may be like this, but there is a steady state error. So this steady state error is existing in the balanced truncation. To overcome these techniques, I have used the balanced truncation technique with the Pi approximation technique. Means here I am going to determine the balanced truncation technique I am going to use for determining the reduced order models, denominator polynomial, and then Pi approximation technique has been used for calculating the numerator polynomial of the reduced model, so that we can overcome this steady state problem of balance truncation. So how you can do this? So first you have to learn the balance truncation, and then we will merge it with the Parde approximation technique. So in the balance truncation technique, first step is you have to determine the controllability and observability gradients. So what is the controllability and observability gradients? So like controllability and observability properties, everyone is knowing that a system is said to be like controllable if you can transfer a system from one state to another state. Similarly, a system is observable if you can determine the initial values by measuring input and output within a certain time. So the controllability and observability gradients is measure the strength of the controllability and observability, how much system or particular system is controllable and how much it is observable. So that is called observability and controllability gradients. So what are the properties of these gradients? So controllability and observability gradients are variant under coordinate transformation. If you will transfer the system, then its controllability and observability gradients are also variable. Controllability observability gradients follows the commutative law, and it is for the balanced system. Means if a system is balanced, then for that system controllability observability gradients will be the equal, and it is diagonal. Similarly, the controllability and observability gradients are always symmetric and partially definite metrics for the stable system. Means if you can check like the system is partially definite metrics, then you can say the system is stable. Means if you don't know the route stability method, but you know the if you know the controllability and observability gradients matrix, then you can simply check whether that matrix is partially definite or not. If the matrix is partially definite as well as symmetric, then you can say that that system is stable. No need to apply route stability method for checking the stability. Similarly, if your system is like unstable but it is controllable, then you can also determine the controllability gradient by using equation 3.6.3. And the next step is Cholesky factorization. Means if your matrix, like if you know the matrix which is having positive definite matrix, then you can convert it into a lower triangular matrix. Why we are going to convert lower triangular matrix? Because we have to determine the similarity transformation matrix, and that we will discuss in this here. So next step is also you have to learn in the balanced truncation, that is called singular value decomposition. So singular value decomposition is only means used for the factorization of a non-square matrix into the square matrix. So here these like A is matrix which is having order m cross n, so you can convert it into square matrix. This is the square matrix, this is the square matrix, and this is the diagonal matrix. So these diagonal matrix is very important. On the basis of this diagonal matrix, we are going to reduce the transfer function. So for the reduction of rth, like if you are going to reduce nth order system into the rth order system, then there must be like r plus 1th anchor singular value much greater than the sigma r. So here sigma 1 is greater than sigma 2, sigma 3, and sigma r is greater than sigma r plus 1. But for rth order reduced model, there should be very no, sorry, wrong. Okay, so it will be very high. If it is not correct, if it is not holding that like sigma r plus 1 is not much less than the sigma r, then you will get the steady state error. To overcome that steady state error, I have proposed the model order reduction and the modified balanced regression technique. So next is balance realization. So what is the balance realization? Means when you can say the system is balanced. The system is balanced when the diagonal matrix is same as the controllability matrix and observability matrix. When the controllability and observability matrix are same, then you can say the system is balanced. So how will you calculate the controllability of observability gradients and how you can implement balanced truncation methods? So I have discussed here. So first step is you have to use the Lyapunov equations for calculating the controllability and observability gradient matrix. So here you can say like in this step 1, A is the system matrix of the Wagner system, B is a control matrix of the Wagner system, which is known. So you can calculate WC by using these equations. Similarly, by step 2, you can calculate the observability matrix by using this polynomial equations. So here, after calculating the controllability and observability gradients, you have to use the Cholesky factorization for converting this matrix into a lower triangular matrix. So is it possible you can convert this matrix into lower triangular matrix? Yeah, it may be possible if both controllability and observability gradients are positive definite matrix and symmetric. If both are not positive and positive definite matrix, it means that the system is unstable. And if system is unstable, then you cannot use balanced truncation method. Balanced truncation method is limited for the stable system. And if the system is stable, then controllability and observability gradients will be definitely positive and symmetric definite matrix. And if it is positive and symmetric definite matrix, then definitely you can convert these matrix into a lower triangular matrix, and that is called like Cholesky factorization. After doing the Cholesky factorization, you can convert these lower triangular matrices into a square matrices, and after converting these square matrices, we can calculate the similarity transformation matrix. And by using this similarity transformation matrix, we can transfer your unbalanced system, like which is defined by matrices A, B, C, D, we can convert into the balanced system. Once the system is balanced, then the controllability and observability gradients will be equal. And then if it is balanced, then you can break your system matrix, control matrix, and output matrix, transmission matrix into part, into the subpart. And by using this subpart, you can determine your reduced model by using a balanced truncation method. So here these are the representing the your state space model of the reduced model by using balanced truncation technique. So here, so by using here this system matrix of the reduced model, we can determine the characteristic polynomial. So after determining the characteristic polynomial, then I will use balanced truncation, Paré approximation method for overcoming the steady state problem of the balanced truncation. So in the Paré approximation method, what you have to do, you have to first expand your original systems as a Taylor series expansion about s is equal to 0. So these are the polynomials C0, C1, C2 that is called the time moment polynomial. And this we can determine by using Taylor series expansion. Once you have calculated these, then you can mix these balanced truncation technique with the Paré approximation technique. How? So these are the polynomials which is known because it is just Taylor series expansion of the original system, which we can easily done by using MATLAB, or you can do manually also. So how to calculate C0, C1? It is given in the like Paré approximation method and as well as in the time moment matching method, how to calculate C0, C1. Also, you can calculate C0, C1 by using Routh stability method also. So there is another like topic. So next is you can calculate PRS. PRS is the denominator polynomial of the reduced model, which we have calculated by using balanced truncation method. And then QRS we can compare, we can just multiply here and then we can compare QRS and we can get the what is the coefficients of the numerator polynomial of the reduced model. So once you have calculated the numerator polynomial of the reduced model, so you can get the reduced order model and then you can compare with that reduced order model with the other existing techniques. If you so here I have implemented our proposed method with the single area power system model, which I already told this is the system which has been modeled in the reference 9 and 11. So after so we will use first balanced truncation method for calculating the denominator polynomial. So for calculating the denominator polynomial, first step is you have to calculate the controllability and observability gradients. So for calculating the controllability and observability gradients, you have to use Lyapunov equation as mentioned in the previous slides. So by using that Lyapunov's equations, we have calculated controllability and observability gradients for this system. So here you can see this. So if you will determine the poles of this system, so poles are these systems are lying in the left half of S plane. So these are the stable systems. So if this system is stable, so the controllability and observability gradients must be partially definite matrix and symmetric. So you can see here you can check whether the system is symmetric or not. So here you can check, yeah, it is symmetric. And how it is partially definite matrix? So you can just determine the eigenvalues. If all the eigenvalues are positive, you can say it is partially definite matrix. So if you will determine the eigenvalues of these matrix, definitely you will get positive. And so you can say that these controllability and observability gradients are symmetric as well as partially definite matrix. So the original system for this is stable. And then you can determine the lower order systems by using balanced truncation method. And then after determining the controllability and observability gradients, we have calculated the lower tabular matrices of controllability gradients and observability gradients by using Pulaski factorization. And once you have calculated lower tabular matrices, you can calculate the diagonal matrix as well as V matrix by using singular value decomposition. So diagonal matrix and this matrix you can see here. So in the diagonal matrix you can see like sigma 1 is greater than the sigma 2 and then sigma 2 is greater than sigma 3. So it will automatically arranged. And then for the like if you are going to determine the second order system, so the second order for the second order systems there should be a very high gap. If this gap is not high, then there will be steady state error between the original system and the reduced system obtained by the balanced truncation method. And to overcome that, I have proposed the improved balanced truncation method, which I will discuss, which I'm discussing here. So by using these matrices, you can calculate the similarity transformation matrix, and then once you calculate calculated the similarity transformation matrix, then you can convert your unbalanced system to the balanced system. So these are the balanced system, and now we can partition these matrices so that we can get the desired reduced model. So this is the partitions, and then by using these we can get the reduced order model by using balanced truncation. So these are the reduced order model which is obtained by the balanced truncation method. So by using this system matrix, you can determine the denominator polynomial. So once you have determined the denominator polynomial, so you can calculate the numerator by using par approximation method or any other method. And then if you will calculate this, so you can just write this is the method by which we are getting the reduced order model. And once you have calculated the reduced order model, you can compare your response with the other system's response. So here I have calculated the response of proposed reduced order model with the other existing technique. So what is the here, what unique we are observing here? So if you will see here, the balanced truncation method's response is giving steady state error as compared to the other method. Why? Because if you will see, the sigma 2 is not much higher than sigma 3. So if it is much higher than sigma 3, then only if you will go to determine second order model, then it will be the means steady state value error will be 0. And if it is not, then you will get the steady state error like this. To overcome this, I have proposed the method which is given here. So if you will see that proposed methods and the original system is overlapping at s is equal to 0. So there is at s is equal to infinity. So there is no steady state error. Similarly, you can also compare your method with the other existing methods. So here I have compared in terms of different steady state values as well as integral square error. So you can see the proposed method is giving least error as compared to the other existing method. And approximately all methods are giving steady state value same except the balanced truncation method, because the balanced truncation or similar perturbation which are giving the steady state error. So here steady state error is getting. So to overcome this, the method has been mixed with other techniques, and that is called like improved balanced truncation, which I have discussed here. And then by using that, we are getting the reduced order model. And then, yeah. So these are the slides which I have discussed for the reduction of higher order system, or the conversion of higher order systems into the lower order system. Once you have converted your lower order system, higher order systems into the lower order systems, the next step we are going to do it to design the controller. Means what is the applications? So here I have just designed the controller by using reduced order model. So you can do other applications also, like in the power system stability. Also, you can do the modular reduction in the power system stability analysis, or in other techniques also you can use. So how I have designed the controller by using model order reduction, we are going to learn here. So for designing the controller, first we need some desired values, desired data. Like if system is given, so for that system we have to get these data. So to get these data, that data will be given. So with the help of that data, we will construct the reference model, or we will construct the reference system. And then our closed loop system must give the same response as the reference model. And reference model, how we have calculated? Reference model we have calculated on the basis of data of your requirement. Like you have to convert, you have to design a system which is giving this much settling time, this much peak time, and this much error. So by using these data, you have to convert the reference model, and then in your systems, you have to design the controller so that the response of reference model and the response of closed loop system will be the same. If it is same, then you are success. So how we are doing this in the reduced order model, that I'm going to discuss. So first you have to calculate the reference model by on the basis of your desired data. And once you have calculated the reference model, then you have to determine the open loop reference model, and that is given in the step 1. In the second step, we have to assume the controller. So here in the equation 7.2, I assume that the controller structure is this. You may assume some other structure also, like you can assume like PID controller, or you may assume like compensator, lead compensator, lag compensator, or lead lag compensator, depending upon the requirements what controller you are going to design. So these are the transfer function of your controller, and these are the transfer function of your reference model, and this reference model they have converted into the open loop reference model. Then in the third step, we are going to see what will be happening here. In the third step, we have assumed that the response of open loop reference system is same as the response of closed loop systems. So, these are the response. If it is matching, then you can determine the controller structure. So here what is given here, this is the controller structure which is unknown. This is the transfer function of original system, higher order systems, which is known, and MS, which is the open loop reference model, that also known, that you have calculated by the known parameters. So these, by comparing these, you may get this equation, and then you can use Taylor series expansion. So you will get this equation 7.5. So by solving these simultaneous equations, you may get the unknown parameters of the controller. So once you will get the unknown parameters of the controller, then you can design the closed loop system. So this is your system, and this is the controller, and then this is the closed loop response of the controller. So here you can see we are determining the controller by using original system. So original system is like, if it is order of 10th or order of 100, then it will be very complicated, and it is very difficult to determine the GCS. System is very complicated. So what we can do, instead of this GS, we can determine controller parameters by replacing this GS by RS, and RS is the reduced order model obtained by some model order reduction techniques, and then you can design, you can implement that controller in the original system. And this is the closed loop response. This is the closed loop model of the your plant, in which controller is designed by using reduced order model instead of controller is designed by the original system. So here controller is designed by the original system, here controller is designed by the reduced system. So here, if you will design the controller by using reduced system, so you can compare. And if you are getting same response, then why we will go to design the controller by original systems? We can design by using reduced system, and then we can implement in the original system, and we can means we can implement that controller in the original system, and we can save the time, simulation, etc. So here I have designed the controller for a flexible missile system. So what is the aim of this? So it should give the natural frequencies like 10 radian, and damping ratio is this. So by using these data, I have constructed the reference model, and this is the transfer function of the original system. So once you have calculated the reference model, then you can calculate the open loop reference system. So once you have calculated the open loop reference system, so you can compare, you can put in this equation. And once you will put in this equation, so because we are going to design the PID controller, so the PID's controller structure is this. This is the PID's controller. You can convert this in that form. So if you will convert in that form, so we are getting this. So from this compare, you can get what is the value of Kp, Ki, and Kd. Similarly, if you know the Kp, Ki, Kid value, then you can implement the controller with the original system, and this is the closed loop response of the original system closed loop. And now next step is we have to convert this original system by a reduced model. If you can convert this original system into a reduced model, then this reduced order model we can use to convert into that can be used in order to design the controller. So here I have used this is the reference model that is the same, and this is the instead of original system we are using reduced model, and this is the KPKI KID values transfer function. So if you will convert this into this form, so you can write in this form, then you can compare. So if you will compare, then you will get KPKI KD value. So if you will see what is the values of KPKI KD here, means here you are determining, here you are getting the value of KP, KI and KD by using reduced system. And if you will see the KP, KI, KD value which you are getting by using version system. So if you will see the both the parameters, means both the controllers parameters are approximately same. So if it is same, then why we will use going for the complicated? We can use simple original systems, and then we can convert it into simple equivalent reduced model, and then by using simple equivalent reduced model, you can design the controller, and these controllers you can implement in the original system, and then this original system will give the same response as you are required. So our requirement is 10 radian and damping ratio should be this, and so if you will compare, so you will get approximately the same response as the original system. So here the original reference model is this. So means our desired parameters is like rise time should be this, settling time should be this, peak value should be this, and peak time should be this. So if you will design the controller by using original system, so you are getting approximately the same response. And if you will design the controller by using proposed method, so you are also getting the same response. So if we are getting the same response, then why we will waste our time to calculate the controller by using original system? We can use reduced order system, and then we can design the controller, and then that controller we can implement in the real-time original systems. And if you will see the response in terms of time domain, so here you can see the response. So here this is the reference system, green one is the reference system response, and if you will go the design of controller by using proposed technique, that is given blue one, so both the response are overlapping. So if both the response are overlapping, so you can design the controller by using reduced order model, so that you can save the time, you can save the calculation, you can save the memories, etc. So here I have designed the controller for the like helicopter engines, which is here transfer function is given, and this transfer function is taken from the reference number 49, in which mathematical modeling is done for the helicopter engine. So from there I had directly taken the transfer function, and in this it is also mentioned that the reference model should be this, and the reference model should be this means by using some desired parameters data, reference model is constructed. Once the reference model is known, so you can just convert it into the open loop reference model, and then you can determine the controller structure by using this equation. So once you will compare these equations, then you can get the values of k, k1, k2. These are the compensator parameters values. So these are the compensator parameters values which you are calculated by using virginal systems. So these virginal systems, if it is very complicated, then it is difficult to get the values of k, k1, k2. So if we will use a reduced order model, like instead of a higher order system, we can just use second order system. This is the reference model. This is the reduced order model. So if you will put in that in the Taylor series expansion, so you will get the what is the values of k, k1, k2, and if you will see these k1, k2 values which is obtained by using reduced model is approximately similar as the k1, k2 values which we have calculated by using original system. So if it is same, then instead of calculating the controller parameters by using original system, we can calculate by using reduced order model. So once reduced order model is calculated, then we can implement it in the original system, which is given like in the equation 7.2, and then you can see the response. So here the response is same as the response of the reference model. So means whatever our requirement is there, we are getting by using closed loop response. So here you can see the response of the original systems, controller obtained by the original systems, and the controller obtained by the reduced order proposed method. All these three responses are overlapping. So, okay, and these are the comparison of in terms of time domain specifications. So for the reference model, these are the desired specifications. Means you have to design the system which should give the rise time this much, settling time this much, peak time this much. So if you will design the controller by using versional system, so we are getting these values. So similar values we can also get by using controller design by using reduced model. So if you will get the similar values as you are getting by designing a control by versional system, so instead of designing the control by versional system, we can design by using a simple system so that you can calculate with less error, with less time, with less computation. So now I'm going to conclude my talk. So in this talks, I have discussed some techniques like two approaches. One is in the frequency domain, and other approaches I have discussed in the time domain. And then here, whatever the methods I have discussed, which are overcoming the existing methods of the convenient method. And then I have also used like pole clustering methods. That methods I have also extended for the designing of the controller and compensator as application of model order reduction. So what are the feature scopes in the model order reduction? So like here, whatever the methods I have discussed, these methods I haven't implemented with the optimization technique. So these techniques we can implement, we can use with the optimization techniques so that we can claim as a new works and then we can get the publications. Yeah, some other techniques like here I have used the techniques for the continuous time domain. So we can use either bilinear transformation or some other direct. We can extend these techniques for the discrete time systems also, and then we can get the publications. And then like we can also use this model order reduction technique in not only for the controller design, we can also use for the fault diagnosis and fault tolerant control for the highly automated and critical systems in which like some systems like some components are less important, so we can ignore and then we can use the concept of model order reduction technique and then we can make automation of that systems. So these are the references from where I have prepared these slides. So thank you, and if you are having doubts, so you can ask in the chat box or you can ask unmute and you can ask also. So there is a like error. Yes, distribution. Yeah, so there is some questions as mentioned in the chat box. So one is like route methods are applicable for the memo system. Yes, so we can use route stability method for the multivariable systems also. Means in the multivariable systems you can get the you can express in the transfer function matrices, and then each transfer function matrices you can apply route stability technique in the numerator and denominator of each components of transfer function matrices of the original system, and then you can write the transfer function matrices of the reduced systems, and then you can get the reduced order model. And there is error RMSC or some error distribution. So here in this, like I have calculated the error, that is like integral square error and relative integral square, absolute error and absolute time error. So these errors I have calculated on the basis of like step response of the original system, and then I have determined with the help with the reduced order model, and then I have compared. So these are yeah. Yeah. So here I have calculated the integral square error and relative integral square error. So by using these formulas, so here y and yr is nothing but the step response of the original system and the step response of the reduced system respectively. Yeah. So any other doubts if you are having, you may ask.
Hello. If anyone has any question, can ask.
So yes, if anyone is having further any doubts, you can ask. Otherwise, we can close today's session and we can meet tomorrow for another session.
Thank you, sir. for your insight lecture on
So I
the
think
topic
there is
reduce
no
order
any
modeling.
questions from the audience. Yes, any questions from the audience side? Oh,
Sir,
yeah,
me Vikas.
just a minute.
Thank you,
Yeah,
sir. Thank you, sir,
yeah,
for
yeah.
your
Anyone
insight
speak?
lecture on the insightful lecture on the topic reduce order modeling and control design. It was the indeed a very informative and inspiring session. I believe the audience has gained the valuable knowledge and will be highly benefited from your thoughts and experiences. We are truly grateful for your times you took to share your expertise with us. Thank you once again for your wonderful sessions. Thank you, sir.